This video is brought to you by thepuzzler.com. Homework for today's class will be available at thepuzzler.com/AMC-8-bootcamp. Let's start with today's class. At any time during the class, you can ask any questions or answer any of the questions on the screen using the chat feature. Okay, hello everyone. Just a quick audio check. Any audio issues before we get started? Just want to take a quick look. Okay. So today we'll be looking at how to find the area of complex shapes. That's going to be the focus for today's class. Let's take a look. So just some basic shapes, right? How to find the area of basic shapes. That's what we're going to be doing. After that, we're going to be looking at the area of these basic shapes, right, into advanced AMC 8 problems. So we'll look at how to break the AMC 8 problems into these basic shapes and find the area of them. So we have triangles, right? Triangles are simple. The area is 1/2 times the base times the height. Okay, so there's some audio issues. Let's see. Okay, so I hope you guys can hear me fine right now. And in the chat, I seem to be seeing no audio issues. Okay, great. So the area is just 1/2 times base times height. That's it for triangles because we've already covered triangles in a lot of the previous classes. What about when we have rectangles? So for a rectangle, we look at the width times the height. And the area is equal to base times height, right? So in this case, the base is equal to the width. So this is base, and this is height, right? So the area is simply base times height. And this is for a rectangle, which means that it has a right angle. Okay, now let's move on to the next shape, trapezoids. So the area of a trapezoid is 1/2 times a plus b. So what's a plus b? This is a, and this is b, right? So 1/2 times a plus b. So the first base is a, and the second base is b. So this is a plus b. And now h is going to be the height. So if I were to draw a line straight down here, and this is a right angle, right? Because it's the height. This is the height. So the area of a trapezoid is 1/2 times a plus b. So we're basically taking the average of a plus b, or of a and b, and we multiply it by the height. And that gives us the area of a trapezoid. A parallelogram, it's pretty easy. Similarly, base times height, right? Base times height. This side is not the height. The height is, you have to make sure you do this correctly. That height is the line that makes the 90-degree angle. That's the height, not this diagonal side. So this is going to be the height. So base times height. And basically the logic of that is we can take this triangle right here. We can cut it off and put it back here. We can just put it back here, right? And we have a square, right? This is some portion that is still here. So the base is b and our height is still h. Okay, circles. So circles, they appear a lot in the AMC 8. And how do we cover circles? Well, the area of a circle, a lot of us probably know this, is just pi times r squared, where r is the radius. The circumference is 2 times pi times r. And then more importantly, or not more importantly, but just as important, is sectors. A sector is just a portion of a circle, right? A piece of pie, you can say. And how do you find the area of the circle or of a sector? The angle that the sector is involving in radians, right? So in radians in a circle, there's 2 pi radians in total, right? So just like there's 360 degrees, there's 2 pi radians. So if I wanted to convert degrees into radians, what would I do? I have 360 degrees. I would multiply by pi and I would divide by, I would multiply by pi and I would divide by 2. Or I would divide by 180. And this gives me 2 pi. So 2 pi radians, right? So say I have 180 degrees. How many radians is that, I might wonder? 180 times pi over 180. 180 cancels. And that gives us pi radians, right? So 180 degrees equals pi radians. And vice versa, right? You can just multiply by 180 for pi if you want to do that. So the area of a sector is 1/2 times r squared times pi. Or times theta, right? And theta is this angle, and that is in radians. Let's try converting this formula into theta in degrees. So we have 1/2 times r squared times theta, right? And we multiply by 180 over pi. So that just means, what does it mean? That means that we have r squared theta times 90 over pi, right? Is this what we have? Let's check. So if we have a circle, someone said in the chat radians. No, not radians. It would be radians. So that would be radians. And it's just a separate unit of measurement, right? Just like degrees, radians are a separate unit of measurement. And we say that there's, in a circle, there's 2 pi radians, right? In a circle, you could say there's 360 degrees, or you can say there's 2 pi radians. Okay, so the last part doesn't even necessarily matter. I'm going to even erase this. Doesn't even matter if it's correct or not. What we're going to do here then is move on. Let's look at this in problems, and it'll all start making more sense. So we won't start out with circles. We'll start out with some simpler problems initially. 3 identical circles are put together to form rectangle ABCD as shown in the figure below. Given that the length of the shorter side of each of the smaller rectangles is 5 feet, what is the area in square feet of rectangle ABCD? I'll give you 60 seconds to solve this problem. It's just a basic problem to get started. So for this problem, you want to start labeling all the sides that you know, right? All the sides that you know, start labeling them. And basically, how do we find the area of a rectangle? We multiply the width times the height. If you can find the width, or if you find the width and the height, you would be able to find the area of the total big rectangle ABCD. I'm seeing E in the chat, 150 is the answer. We'll see. Let's see how to do this. So this problem, it was on the easier end of the AMC 8. We have that given that the length of the shorter side, so the shorter side of each of the smaller rectangles, that's 5 feet. So let's put that in 5, 5, 5. But wait a second. DA is 5 plus 5. So the total height, or CB, is 10. Similarly, this is also 10, right? All of these rectangles are the same, because it says 3 identical rectangles. So we have 15 times 10 gives us 150. No units needed. Our answer is 150. In the diagram below, a diameter of each of the 2 smaller circles is a radius of the larger circle. If the 2 smaller circles have a combined area of 1 square unit, then what is the area of the shaded region in square units? Okay. So I don't really know what the radius of the circle is, right? I can calculate it, or of any of the circles, I can calculate it. Let's see. The two small circles have a combined radian area of 1 square unit. Okay. So then let's say this is r. I can just say pi r squared if this is r. And then there's two of them, and this is equal to 1, and so on, so on, so on. Who cares, right? You could do that. You can find the value of r, then find the value of the diameter, which is the radius of the bigger circle, subtract that, whatever. What I'm going to do is, I know this is r. So the area of this circle is pi r squared. There's two of them. So the total area is 2 pi r squared. So of the two white circles, the total area is 2 pi r squared. Now the diameter is 2r. And this is the radius of the bigger circle that's partially shaded, right? So 2r squared times pi. And this is 4r, I'll write in the same format, 4 pi r squared. So we have that 2 pi r squared is the white area, and 4 pi r squared is the total circle, right? So 4 pi r squared is the total area. If I want to find the black part, I just subtract the white part, 2 pi r squared. And this gives us 2 pi r squared. So the other parts are also equal to, so the shaded black part is also equal to 2 pi r squared. Our initial white stuff is equal to 2 pi r squared. Our black stuff is equal to 2 pi r squared. The white circles we already know are equal to 1 square unit. And since it's the same for both, the black part is also equal to 1 unit. And we move on without ever finding the value of r. Now this problem we've looked at before in a previous class, but it's a good review problem, right? And it doesn't exactly... It involves us actually finding the side lengths first and then finding the height of the triangle, right? When you want to find the area of a triangle, there's a lot of different ways, but the main way is base times height divided by 2. So let's see. So my first hint is to draw point D, right? I'll give you a hint. You can find the length of CD and DB. Okay, I'm seeing a lot of good answers. That means that a lot of people remember how to do this problem. That's a good sign. Okay, so for this problem, what do we have? We have a point D. A point D somewhere here. I don't know where to draw it. Maybe I'll draw it somewhere here, right? Right around the middle, even though it's not exactly the middle. So we have, this point is D. This is, say, Y. This is X. What is this? Well, I can introduce a third variable, Z. But I know this is 5 minus X, right? Since the total side is equal to X, or is equal to 5, these two, DB and CD, must add up to 5. So what do we have? We have two parameters. We have that 3 plus Y plus X is equal to 4 plus 5 minus X plus Y. So notice that the length of Y doesn't matter. It's the same in both. So that doesn't even matter. Now we can do everything else. 3 plus X equals 4 plus 5 minus X. And this is a linear equation. We can find the value of X. We have that X is equal to 4 plus 5 is 9. 9 minus 3 is 6 minus X. So 2X equals 6. X equals 3. This is 3. Plugging in 3 here, we get 2. Okay. So now what? Now we have, let's see. Now we have two side lengths. We have 2, 4, of this triangle. So I know the base, right? The base is 4, but I don't really know how to calculate this height. I also know that if I were to look at it from dB being the base, then I also don't know how to calculate the height. Let's see. Well, what if I look at the triangle ABC as a whole, right? If I look at triangle ABC as a whole, the area of triangle ABC is just the base, which is 4, times the height, which is 3, divided by 2. This is 6. The base is 5, right? If I now flip this triangle around and now I look at it from the perspective of the hypotenuse, or the longest side being the base, then I'll have something else. Now, say the height is this, right? So this is the height, and this creates a right angle, and let's call the height h. We have that 5 times h divided by 2. Well, that's still equal to 6 because the triangle is the same. So then we have 12, right? I multiplied both sides by 2 and divide both sides by 5 to get 12 over 5 equals h. So the height, well, the height is just equal to 12 over 5. And same thing for triangle ADB. It doesn't shift. Base is still the same. AB is still the same. The height is still 12 fifths. So we have 12 fifths as the height. The base is 2. So the base is what changed from that original triangle. And then we divide by 2 or multiply by 1/2. And like most of us said in the chat, the answer is 12 fifths. Okay, getting a bit harder now. I think I would say this is around to number 16. In the non-convex quad ABCD shown below, angle BCD is a right angle. AB equals 12, BC equals 4, CD equals 3, and AD equals 13. What is the area of quad ABCD? So this one, we will actually be incorporating a bit of the Pythagorean theorem to find some stuff. But in essence, this is an area problem, right? So this is where I'm going to not just be finding the area of simple stuff. This is not a simple shape. I don't know how to find the area of this. I don't have any formula. I know all 4 sides actually, but I still don't have a formula. What's non-convex? So that just means that there's angles that are more than 180 degrees. So usually we're only dealing with convex quads, right? That means that all the angles are less than 180 degrees. Rarely will you see a quad like this, but this would be a concave quad, or you can say non-convex. It doesn't really matter for this problem, actually. It doesn't make a difference if they mention that or not. They just want to make sure you have an accurate sense of what the diagram is. Yep, Leonardo, you're correct. Okay, let me give you guys 60 seconds to solve this problem. Okay, this is good that you guys are finding this one easy. And it's okay if you're not. We're going to learn how to solve it. Important thing is drawing in lines, right? And then we'll be able to think of this in terms of stuff that we don't already know. Okay, almost done with the time. Okay, so an important part of tackling problems like these is drawing in lines, right? You have to draw in auxiliary lines, right? These are lines that are not actually there in the problem. You draw these lines in to help make the problem super easy to solve. And here's what I'm talking about. So we know that this is a right angle. AB equals 12, BC equals 4, DC equals 3. Oh, wait a second. DCB is a right triangle. But we don't have DB. Let's draw it in. And this is a right angle here, right? It's approximately straight. So we have 3, 4, and AD equals 13. So I'm not actually gonna, I did say it's approximately straight, but that doesn't tell us that it has to be a right angle, right? If you think about it, approximately straight, but that just might be because I drew it that way. Um, what do we have here? We have that DBC is a right triangle, right? Legs are 3 and 4. A few weeks back, I told you to memorize a few Pythagorean triples. 3, 4, and 5 was one of them. So DB is 5. I also asked you to memorize the 5, 12, 13 triple. So that means that ABD is a right triangle because its legs and hypotenuse satisfy the Pythagorean theorem. So what is this total thing? What is DBA? Well, we can think of DBA, or we can think of the quad that we're trying to find, DCBA, as the triangle DBA, the whole triangle DBA, minus this portion. So if we subtract that portion, we're just looking at the quad that we want to find the area of, and that's this quad. So we can do that. The area of DBA, that's 5 times 12 divided by 2, so that would be 30. The area of DCB, well, that's 3 times 4 divided by 2, so that would be 6. 30 minus 24 equals 6. So our final answer, or 30 minus 6 equals 24. So our final answer is 24, and we're good to go. Okay. Trapezoids. So quad ABCD is a trapezoid. AD equals 15, AB equals 50, BC equals 20, and the altitude is 12. So basically, we just need the length of the two bases to find the area in this case, but we don't have the second base, so that might be a problem. What is the area of the trapezoid? I'll give you a minute to try it. Try to break up the bottom base into parts that you can find the length of, right? And that will help you a lot. That will actually help you find the actual area of the trapezoid. By the way, if you haven't already, please give this video a like. We are giving you guys these free classes, right? And they take a lot of effort on our end. And all we ask is, if you haven't already subscribed to our channel, subscribe. And please give this video a like so that other people could find it using the YouTube algorithm. Okay, thanks to everyone who just gave the video a like. And it's okay if you haven't yet. Maybe after a problem or two, you'll change your mind. Okay, so for this problem, a lot of people got the answer, but guys, something that I want you to try and do is that if you have time, why not write out some sort of explanation, right? So that we know that you didn't just copy pasta, you didn't just really take someone else's answer and write it down, right? It's a multiple choice question, so obviously you have a 1/5 chance of being correct, even if you guess. So just try to provide me a quick sentence or two. So what do we have here? We have to find DC, right? That's the only way to find the area of this trapezoid. Sum up the bases, multiply by half, and then multiply by 12. Or that's the simplest way, right? Every other way still requires us to find the base. Well, once again, I'm going to draw in a line. I just drew the altitude. That's 12. This is 12. I'm going to do the same on this side. This is a right angle again. This is 12. And now wait a second. Pythagorean theorem again. Our classes are all cumulative, right? They all build on each other. We have to use the Pythagorean theorem again. This is 20, this is 12. So this is 16, right? It's just 12, 16, 20 Pythagorean triple. And this is actually the 3, 4, 5 Pythagorean triple, just a multiple of that. And then same thing here, 3, 4, 5 Pythagorean triple. We multiplied by 3 this time. That gives us 9 here. And AB, well, that just carries down. That's the whole thing is 50. So we have that 50 plus, what's 50 plus 9? That's 59. 59 plus 16, what is that? That is 75. 50 plus 75 times 1/2 times 12. That's, what is that? That's 125 times 12 divided by 2 is 6. That's 250 times 3. And we all know that is 750. Okay. Okay. So we have this problem. I think this problem was a number 25, if I'm not wrong. So this is a hard one, right? And it's fine if you can't solve this, but this problem is a number 25. So let me read out loud. A semicircle is inscribed in an isosceles triangle with base 16 and height 15, so that the diameter of the semicircle is contained in the base of the triangle as shown. What is the radius of this semicircle? I think this isn't an area question, but I think this was a good problem to put in here because it really shows us the power of just like putting in auxiliary lines, right? Lines that are not already there, put them in and see what you find. Okay. Now, I don't see too many answers yet for this problem in the chat, so I'm going to give you guys another minute or two to try and solve it. So let me just restart the timer. Just another minute or two. Try your best, right? If I still don't see enough answers after this minute, I'll give you another. Try providing me an explanation in the chat instead of just writing B, right? Because you might have seen one person do it, and then just put down your answer. So try providing me a brief explanation if you know how to do it. Okay, let's see how to do this problem. I still don't see too many answers, but I think that's good, right? What I'm gonna do right now, I'm gonna go over this problem. It's okay if you can't do it, because it's a number 25, right? So if you can do this in less than 1 minute without ever seeing this before, that's great. That's a very good sign for the AMC8. If not, then it's time for you to pay attention, right? So that we can try solving this problem. So yeah, first thing, just like Alex mentioned, we're going to be dropping in altitude. And I wouldn't say dropping this in altitude. I would say we're putting back the information that they gave us. They told us that this is 15, right? Except if you were referring to the other altitude that we're going to put in later in. That's great, Alex. So then we have the base is 16 divided into 2, so that gives us 8 and 8. Okay, what do we have after that? Then we have, what do we have? Well, now I'm going to tell you another very important property. Whenever we have a circle, so let's say I drew a circle, and then we have a line that's tangent to it. So a tangent line to a circle is a line that only touches a circle at one point. So most lines would touch a circle at 0 points, which means it never intersects, or 2 points, which means that it goes through. Well, here, it only touches at 1 point, right? And that's possible. Look at this right here. It only touches at 1 point, right? So if you draw a line from the middle of the circle to the point where the tangent line is touching the circle, well, the radius makes a 90-degree angle with the tangent. And that's just something that you should know, pops up in the AMC8 a lot, like here. And we can actually use that. That makes this problem very simple. Or not very simple, but simple enough. So I'm going to do it on this side. Okay. Now, notice first of all that this is a right triangle, right? We split an isosceles triangle in half. That's a right triangle. 8, 15, and 17. That's another one of the Pythagorean theorems or triples that I told you to memorize. So I'm going to write that here. This is 17. This whole thing is 17. Okay, so what do we have now? Let's see. Well, does anyone notice any similar triangles? Let me draw this in. This might help. We notice a triangle. Let me label these points. A, B, C, D. So we notice that triangle ABC has a right angle and it has this angle. Triangle ADC has a right angle and it has this angle. Wait a second. We learned about similar triangles. They're similar by double angle similarity. So that means that these angles are similar. More specifically, we have that angle ADC is similar to angle ACB. Okay, and now we can do a lot of stuff. First of all, we have, what do we have? We have that, I'm just going to write them all out. AD over AC is equal to AC over AB. And then that's equal to DC over CB. Well, I don't know the measure of AD, right? If I knew that, that would be easy because then I can just find this using the Pythagorean theorem. I don't know that. So I crossed this one out. AC over AB, well, I know AC. AC is 8. AB, well, AB, I just told you, using the Pythagorean theorem, we found it's 17. What about DC? We don't know DC, that's what we're trying to find. CB, oh well, CB is 15. And now we can multiply both sides by 15. And what do we get? We get 15 times 8, which is 30 times 4, or 60 times 2. And that gives us 120 over 17 is equal to DC. So this isn't an area question, but it's just so cool that I put in one line that they gave us. This line is something that a lot of us would be able to do. And I drew in another line right here, DC. And that basically helped us solve the problem using similar triangles. So that's great. And now, giveaway winners. So Alberto Jernan won and Rishi Kanchi won last week's giveaway. And they both won 2 interview cake module accesses valued at $169 each. So I'll be giving you guys a minute to enter this week's giveaway right now. And you can go to thepuzzler.com/AMC-8-bootcamp-giveaway to enter that. You can also find a link of that in the description below. So I'll give you a minute right now. If you don't want to enter right now or don't think you have enough time, you can always enter after the class. This would also be a good time to ask me any questions that you have so far. Okay, so Colin, how does that match up with the radius? That's your question. Let's see. I'll go back while people are still entering the giveaway. Oh, DC is the radius, right? We defined it to be the radius. And it tells us that the line intersects the circle at one place. And where does it tell us? It tells us inscribed. And that's what inscribed means by definition, right? These both lines are tangent lines. Vihan, yes, previous winners can win the giveaway again, right? We just use a random number generator, so they could win the giveaway again. Yep. So, time's up to enter the giveaway. Let's go back to the next problem. 1-inch squares are cut from the corners of this 5-inch square. What is the area in square inches of the largest square that can be fitted into the remaining space? Okay, so this problem, I don't think there's only one square that's going to have the largest area, right? This area might be shared in different squares. I might be wrong, but just make sure that you think of that. You don't have to find the exact square. Just think about what the best case scenario would be. So let's see. I did put a sticky note there if you noticed. And once I remove that sticky note, you'll see a very useful diagram. That's going to really help you out. About 8 seconds left. And let me reveal the diagram. Delete. Okay. I think this is something that's going to really help you guys. So this problem, I noticed that I didn't see any answers actually. Okay, I'm seeing a few now. JC and Jignesh, but those are different answers. So I drew a diagram here. In the best case scenario, we'll be including this whole middle square area plus these red triangles, right? And notice that the height of the red triangles is always 1 and the base is always the same. So even if, like, say the point of this triangle was somewhere here, right? So if the triangles were drawn like this, it would still be the same area because the base and the height are the same. So that doesn't matter. So what we do is we take this diagram and we draw on it. Total thing is 5 by 5. We cut out 1 by 1. We just try finding the lengths. We just chase around the lengths. This is 1, this is 1, this is 1. Total thing, that's 5. So 5 minus 1, that's 3. And what do we have? We have that this right here is 1. This right here is 3, 1, 1, 3, 1, 1, 3. Okay. So this is 3, this is 3. So the area of the square is 9. The area of the triangle, well, this is 1, right? We said this is 1, so this is 1. We have 3 times 1 divided by 2, and there's 4 of them. So that gives us 6. So 9 plus 6, well, that's just 15. And this problem's that simple. Our answer is 15, guys. Let's move on. Okay. Once again, drawing back in lines really helps. And this is actually going to involve sectors, right? I told you they're going to appear later on. I believe this is a number 25. So in the figure shown, US and UT are line segments, each of length 2 and measure of angle TUS. So I'll write that right here. TUS is 60 degrees. Arcs TR and SR are each 1/6. This is very important. 1/6 of a circle with radius 2. What is the area of the region shown? Try this problem. I don't know if you would be able to solve it in a minute, right? You might get the concept, but doing the actual computation might not be that easy. Let's see. Okay. Don't worry if the timer covers part of the problem. Basically, it's saying that they're both 1/6 of the circle, just so that you guys can see it bigger. Yeah, don't worry about the problem being sort of cut off some. It's fine. It just says are each 1/6 of the circle with radius 2. I just want to make sure that the problem is big enough for you guys. Okay, this problem. We have that, what we have here is a triangle. And look, I just drew in the lines, and once you start doing this enough, you'll notice that. You'll notice that they were hiding a triangle from you. They were hiding a secret triangle from you. Actually, let me make my drawing a bit straight. As straight as I can try at least. Just bear with me for this diagram. And we have this triangle. When it says 1/6 of a circle, well, a total circle has 360 degrees. And we have 360 degrees times 1/6. Now what? We do this and we get 60 degrees. And this is important, right? If we have 1/2 of a circle, that's 1/2 times 360 degrees. We have 1/5 of a circle, that's 1/5 times 360 degrees. Okay, what do we have? We have 1/6 of a circle, that's 60 degrees. This is 60 degrees, this is 60 degrees. Okay, what is this, guys? This is a equilateral triangle. All three angles are the same. That, by definition, is an equilateral triangle. What does that tell us? Well, remember the area of a triangle or of a sector? First, let's find the area of the triangle. This is 2, this is 2, this is 2. All sides are equal, so each side is 4. Remember the formula for an equilateral triangle, and we found this in the last class, is s squared root 3 over 4, where s is the side length. So we have 4 squared root 3 over 4, 16 root 3 over 4 equals 4 square root 3. And we have to subtract these two sectors. Each of these sectors is 60 over 360 degrees, right? So I'm not even using radians here. It's 60 over 360. That's 1/6 of the circle of a 2-inch or 2 length radius circle, right? So we have 2 times 2 times pi. Don't want that to be a triangle, so 2 times 2 times pi, and there's 2 of them, so this gives us 1/6 times 8 pi, or 4/3 pi in total. So we have 4 square root 3, but we don't want the two 1/6 circles, which is 4/3 pi. So this problem is B. Okay, let's move on to the next problem. A circle with radius 1 is inscribed in a square and circumscribed about another square, as shown. Which fraction is closest to the ratio of the circle's shaded area to the area between the two squares? Now for this problem, just make sure you realize what inscribed and circumscribed means, right? So circumscribed would be this dark shaded square. That's the one that's outside the circle. And inscribed means inside the circle. So that would be this white square. Okay, if you know that, you should be able to solve this problem. But we'll see. Okay, I'll give you a full minute to try this. Okay, so for this problem, probably a good idea to find the area of, or the length of both squares. We'll see. Okay. These type of problems, guys, once I solve one of them, these become very easy. Once I solve one of them, you're going to basically get these type of problems. And I actually loved seeing these type of problems on the AMC 8. Because once I saw them, the format of all of them was the same. What do? Draw the radius. That's 1. So this radius is 1, this is 1. Let me also draw in this one, 1. Well, this is 1 then, right? It just carries over, that's 1. So the bigger square, that is 2, right? So the side length of the bigger square is 2. 2 times 2 is 4. That's the easy part. Now, this is a right angle. So this line right here, we can find that using the Pythagorean theorem. 1 squared is 1 plus 1, taking the square root of that is square root 2. So this is square root 2. Square root 2 times square root 2 gives us 2. So the white area is 2. Now it's asking, Which fraction is closest to the ratio of a circle's shaded area to the area between the two squares? Well, the radius of the circle, that's 1, so 1 times pi. So the shaded area is pi for the circle. Pi minus 2, right? Pi minus 2, because we're not including the white part. That doesn't count as shaded. To the area between the two squares. Well, the area between the two squares, that's the bigger square minus the smaller square, or 4 minus 2. So this is pi. Pi is approximately 3.14. We're asked for an approximation here. So 3.14 over 2. And this is not 3.14. 3.14 minus 2. That's 1.14. Over 4 minus 2, that's 2. That's not this, not this, not this. Doesn't look like 1 either. Approximately 1 over 2, right? It's 0.14 extra on the numerator, but approximately 1 over 2. Our answer is A. Okay, so rectangle ABCD has sides CD equals 3, DA equals 5. A circle of radius 1 is centered at A. A circle of radius 2 is centered at B. And a circle of radius 3 is centered at C. Which of the following is closest to the area of the region inside the rectangle but outside all three circles? I think this one people are going to find easier than the problems before or after this, right? We know how to find the area of the quarter circles. I think you guys will be good to go here. We'll see. Let me move the problem down. Okay. So just find the area of each of the quarter circles, and you already know the area of the full rectangle. That's easy. Remember, a quarter circle, that's 1/4, right? That's 90 degrees. These angles are 90 degrees. And how do I know they're 90 degrees to be exact? Well, it's a rectangle. Each angle in the rectangle is 90 degrees. So 90 over 360 gives us 1/4. So the area of those quarter circles is 1/4 of the area of the triangle with the same radius. Or of the circle with the same radius. This is part of our sectors, right? We looked at how to find the area of sectors in the beginning. Okay. So this problem, what do we have? Let's find the total rectangle. That's 5 times 3 gives us 15. What about this one? That's a circle with radius 3. So 3 times pi divided by 4, right? Because it's a quarter circle. So that's 9 pi over 4. This is 2. So 2 times pi times 1/4. 4 cancels, we're left with pi here. What is this? This is 1. It tells us right there. 1 times pi times 1/4 gives us pi over 4. So we have pi plus pi over 4 plus 9 pi over 4. And this is, let me move here. We have 4 pi plus pi, plus pi plus 9 pi over 4. And this gives us 14 pi over 4, or 7 pi over 2. So we have 15 minus 7 pi over 2 here. How do we do 15 minus 7 pi over 2? It's hard to multiply by 3.14. And if you use the calculator, that's also wrong. What you do is never forget pi is approximately 22 over 7. And I think a lot of you forgot about this. This makes it easy. 7 over 2, let me do the math over here. 7 over 2 times 22 over 7. 7's cancel out. 22 over 2 gives us 11. So this is just 15 minus 11. And that we can do without a calculator. That gives us 4 as our final answer. Okay. What is the area of a triangle formed by the lines y equals 5, y equals 1 plus x, and y equals 1 minus x? So let's see. I think this problem is one of those problems where I'll give you guys more than 1 minute, maybe 2 to 3 minutes to try this problem. Right? So let me start the timer. I'll give you guys about 2 to 3 minutes to try and solve this problem. First minute's almost over. So what do we have? Let's see, I'm seeing 2 answers. Yeah, that definitely calls for another minute. Let's give you guys another minute. And I won't just be silent here. I'll start drawing my ugly graph. Okay. I'm just starting to draw. It's fine. Take this time if you need to solve the problem. Once again, guys, we request that if you haven't already, make sure you give this video a like, right? If you're watching this video, just why not just scroll down a bit and hit the like button and make it blue, right? So what do we have here? We have, let's just wait for the timer to finish before I proceed. Okay, we have 3 lines. Let's draw them. Where do they intersect? They're not that hard to draw. 1, 2, 3, 4, 5. That's y equals 5. And then I have 1 plus x, right? So that's going to intersect here. So the y-intercept is 1 plus x for both of them. And it's going to look something like this, right? I'm not actually going to draw in my x points, right? On the actual test, not sure if you guys get graphing paper this year. Obviously, they allowed it in the past, but this year they did put some sort of ban on graphing paper on the AMC 10 and 12. Not sure if they applied that rule to the 8. So what do we have here? We have these lines, right? We have these 2 lines and this 3rd line. How do I find where they intersect? I use a bit of algebra. I'm not going to draw in the points because I don't trust my drawing skills. So we have, where do these 2 lines intersect? Well, they intersect where their y is the same. So we have 5 is equal to 1 plus x, right? Where they intersect, the y and the x point are the same. So the x point is equal to 4. So the first point of intersection, 4 comma 5, that's going to be in the positive plane. That's going to be 4 comma 5. Now, what about these 2? Similarly, that's going to be 5 equals negative 1 plus, or 5 equals 1 minus x. So that's going to give us 4 equals negative x, or that x equals negative 4. So this is just mirrors over here, negative 4 over 5. It mirrors over the y-axis. Finally, the 3rd point is going to be 1 plus x equals 1 minus x. The 1's cancel, so we have x equals negative x, or that x equals 0. Plug back in x equals 0 here, and we get 1 plus 0 equals 1. So this point is 1 comma 0, or 0 comma 1, right? So this point is 0 comma 1. And now this problem, it's very easy once you see this drawing, right? We can just fill in the sides. So I'm going to make some more space here. And what do we have here? This right here, the x-axis tells us that this is 4, right? So since the point is 4, this is also 4. And this is the isosceles triangle, right? Because this right here, this is 5 minus 1. So this is 4. So we have 4 times 4 which is 16 divided by 2, which gives us 8. Or no, that's not correct. We have 4 plus 4, that's 8, right? The base is 8, multiplied by 4 divided by 2, that gives us 32 divided by 2, or 16 as our final answer, right? So this problem, once you draw a picture and you label in the points, you see that it's very easy. Any questions for this problem? No? Okay then, let's move on to our last few problems. Two 4x4 circles squares intersect at right angles, bisecting their intersecting lines as shown. The circle's diameter is the segment between the 2 points of intersection. What is the area of the shaded region created by removing the circle from the squares? Okay, so this problem, I think this is a number 25, and this was one of the hardest problems, right? Even when I was actually doing the AMC8, right? A few years ago when I was doing the AMC8, when I mocked this problem, I found it to be one of the hardest AMC8 problem. So let's see if anyone can solve this one. This problem. You do need to draw in not just extra lines, you need to draw in a full square. Okay, so I'm finding that good that some people in the chat are not finding this hard. Let's see. So we have 4 by 4. So two 4 by 4 circles intersect, or squares intersect at right angles, right? So if you've ever seen two squares, right? I'll draw two squares here as much as I want them to look at squares. They don't look like squares. Okay, one square and the second square. So what you'll notice that when two squares intersect and they bisect, right? This isn't bisection. There's going to be a nice, neat little 1/4 square, right? Because this square, this is, I'm going to draw this in. So this is going to be half and this is going to be half, right? And this is all equal. This is all equal. Each of the sides are 1/2. So what we have here is half squares, right? So what we do here is this is 2 by 2 by 2 by 2. So the common intersecting area, forget about the circle even existing. The common existing area is 16 plus 16, right? The area of the two squares, minus the area they have in common, which is this 2 by 2 square, which is 4. And don't worry if this doesn't make sense. This is a bit hard to imagine, right? You'll get it with practice. So we have 16 plus 16 minus 4, that gives us 28. What's the area of the square now, right? The area of the square is what we don't want. So we have this is 28 minus, well, the square, let's see. The square, if you look at this 2 by 2 square, let me just erase this. If you look at this 2 by 2 square, you'll see that the diameter, so this is 2, this is 2. The diameter can be found using the Pythagorean theorem, which is 2 root 2, so the radius is root 2. Root 2 times pi gives us 2 pi. We don't want that 2 pi circle, right? So we're doing the extra square, and our answer is 28 minus 2 pi. I think we're doing the last problem now. So that problem, we made it look easy. Okay, this is the last problem. I think this was also a number 25. Margie's winning art design is shown. The smallest circle has radius 2 inches, with each successive circle's radius increasing by 2 inches. Which of the following is closest to the percentage of the design that is black? Once again, one final call. If you haven't given this video a like, make sure you do that before you leave today. Okay, so for this problem, I'll give you guys a minute while you think about it. Just think about it. Maybe just do the computation. So for this problem, I'm seeing an answer in the chat, an answer or two, that's good. Let's see what to do. So what we're going to do for this problem is first remove this secret sticky note that I put here to get the table. Okay. So this table, it tells us the measure of each circle, right? The first circle, radius 2, then 4, then 6, then 8, then 10, then 12. And their respective areas are 4 pi, 16 pi, 36 pi, 64 pi, 100 pi, and 144 pi. What are we looking for in total? Well, this 100 pi circle, right? And excuse that drawing. So 100 pi minus 64 pi. That gives us 36 pi. And then what do we have after that? I think we have 36 pi minus 16 pi, right? This circle right here minus this. So 36 minus 16 pi. What does that give us? That gives us 20 pi. And then I think we also have the smallest circle. The smallest circle, right? We're trying to find the percent of the design that's black. That's 4 pi. So we have 60 pi over 144 pi. I'm just doing this really quickly so that we don't go too much over time. But 60 pi over 144 pi. Pi cancels. 60 over 144. Which of the following is closest to the percent of the design that's black? Well, 60 over 144, let's simplify that. Both are divisible by 6, right? So this is 10 over 144 divided by 6. That gives us 2. Is that 24? 6 times 20 is 120. 4 times 6 is, yep. And this is 5 over 12. Okay, 5 over 12, not too hard to calculate. That's going to be what? Well, 1/12 is approximately, let's see, 100 over 12 is approximately, we have 96 as the closest multiple. So what do we have? We have 60 is 5. We have 8.3 repeating is equal to 1/12, right? 8.3 repeating is equal to 1/12. We're asked to find 5/12 as the percentage. Multiply this by 5. We get 8 times 5 is 40. 3 repeating times 5. Well, that's going to give us approximately 1.5 plus something. So this is going to be 41.5-ish, right? That is the closest answer, and we're done. Any more problems? Nope, we're good to go, guys. Today's class was especially challenging, right? We actually had to find the area of complex shapes in so many different ways, adding in different lines, even adding in different shapes, right? And breaking it into stuff that we know. So if you have any questions, feel free to comment it down below. If you did enter the giveaway, or if you have anything interesting to say, don't forget to just comment it down below, and I'll try my best to get to it. Thank you, everyone, and see you all next week. Thank you for watching this video. If you liked this video or learned anything from it, let me know by subscribing or commenting below. For more awesome content, check out thepuzzler.com. You'll find amazing articles and free courses there. Thank you.